Okay, so I turned the tape on. So we're officially starting here, and we usually have a homework due, but we don't have a homework due tonight. So the next homework is not due until Tuesday, next Tuesday. So that's the chain rule homework. And again, that's probably a fairly challenging homework. And we're going to talk today about implicit differentiation. As soon as we finish the last few examples from the chain rule, we're going to talk about implicit differentiation, and then because that's closely related to the chain rule. Implicit differentiation depends a lot on the chain rule, and then that homework's not due till next Thursday, and that is the last thing that is on the. This is the last topic that will be on the next test, right? But we'll be continuing next week with new material. But this is the last thing that will be on the test, which is, as we discussed last time, it is in this announcement on the right-hand side of your WebAssign homework page. That test is on April the 13th, which is Tuesday, the week after next. And the sample test is now posted, right? So your sample test is posted, and probably by today, then we will have pretty much talked about everything that's going to be on the test. So the things on the sample test, at least we will have discussed them in class formally. You won't have finished homework on those things yet, but you'll at least have seen, I think, everything that's on the sample test, and then will be on the test, right, after today. Okay. The homework from that was due on Tuesday. So y'all did pretty good on that. But I did notice there were, because I knew that was a hard homework, so the averages were a little bit lower. But and there were some pretty challenging problems on there. And so I wanted to look at a few of the problems that I looked at that had apparently caused the most issues. So you may have had other problems other than the ones I'm going to point out here that you found difficult, but these are the ones that I think the class was missing the most. Okay. According to WebAssign. I'm not going to open that homework, but I have it. I have those problems somewhere here copied into my notes if I can find the right notes. Oops, I may have closed the right notes here. So let me see if I can find that and open that notes. Okay, let me scroll down here. These are the last few examples from, of the chain rule that we hadn't quite finished last time. So we'll finish those in a minute. But let me go down here and let's see. All right, so here's where I just made some screen captures of some problems, and so we'll talk about these. Okay, so maybe these were the ones that you also found challenging. So I don't know what the number was of these problems in the homework, but let's look at this. Here's the first problem. So now this is a problem that there's probably problems like this on the sample test. So there's probably going to be a problem like this for sure on the test. Okay, maybe not as difficult as this one, but something like this, stated like this, would be on the test. So they give you here a function. In this case, it's x squared over x minus 2, and then they want to know at what points on the graph, could be more than one, where the function has a horizontal tangent line. Okay, so that means almost certainly there that you're going to have, with a horizontal tangent line, right, you're going to have a peak or a valley. So what they're really asking you for here are, where are the peak points, the local maxima on the graph, and where are the valley points, the local minima on the graph. This is an indirect way of asking that question. I made a graph of this function, though. Let's look at that first, just to convince ourselves that this question has an answer, because just because we ask a question doesn't mean it has an answer. So I graphed this function, here in Desmos. So here's a graph of this function x squared over x minus 2. And you can see from the graph, it's got two pieces to it. So there's two branches to the graph. That's because the number 2, x equals 2, is not in the domain of this function. If you try computing f of 2, you end up dividing by 0, which you cannot do, right? So this graph does not cross over x equal 2. So it's not continuous at 2, all right? There's a break here in the graph at x equals 2. And so you get this branch on the left, and then you have this branch on the right, and they're not really very interesting graphs, but there they are. And you notice that you do have here on the left a peak point, right? It appears to be right here at the origin. At 0, 0. So that looks like that's where this left part of the graph peaks out, right? So a local maximum right here. And indeed, it appears that at this point, you have a horizontal tangent line. In fact, it looks like the x-axis itself is the tangent line to the graph right here at 0, 0, right? That's what it appears like to me. That the x-axis itself is the tangent line. So, of course, the x-axis is horizontal, right? So, so here's a point, I think, where we have a horizontal tangent line. And then it looks like right here also, Desmos is trying to signal this point to us as a special point also. And so I think right there, we also, that's 4, 8. So 4 on the x-axis, it looks also right there, we have a horizontal tangent line, right? So this is a local minimum, because this is where the graph is switching from decreasing to increasing. So remember, that's called a local minimum, or I call it a valley turning point informally. And then this is a local maximum, right, where the graph is switching from increasing to decreasing. I call that a peak turning point, okay? But the more technical term is a local maximum. So it looks like, from looking at the graph, right, that we can already see apparently what those two answers are, right? We're going to have a horizontal tangent line at 0, 0, and we're going to have a horizontal tangent line at 4, 8, right? But if you don't have the graph in front of you, right, then how do you do this without the graph? Well, of course, that's where you're going to use the derivative, right? Okay, because remember, the derivative tells you slopes of tangent lines, and we want the slope of a tangent line to be 0, right? Because we're looking for where our tangent line is horizontal, and horizontal lines have slope. Horizontal lines have slope 0. So first things first here, that means we have to find the derivative, right? We have to find the rate of change. So we have to calculate here f prime of x. So that's the first step kind of in this problem, once you've sort of figured out what you're being asked for, right? And so I think to calculate the first derivative here, we're going to use the quotient rule, because this formula is a quotient, right? And so so by this, hopefully by the time you get to this point in the homework, you will have practiced the quotient rule quite a lot. So so you would be pretty relatively quick at doing that by this point. So remember, the way the quotient rule works is you take the derivative of the top times the bottom. Well, the derivative of x squared is 2x. So you have 2x times x minus 2. Just keep the bottom, right? And then minus, don't forget you're subtracting in the quotient rule. And then you keep the top, which is x squared, and you multiply by the derivative of the bottom. But the derivative of the bottom here is easy. The derivative of x minus 2 is just 1, because the derivative of x is 1 and the derivative of minus 2 is 0. So you just get 1 times the x squared. Oh, that's nice. And then remember, you put on the bottom here in the quotient rule the original denominator squared, right? Okay. So I didn't simplify it yet there, but that is the derivative, okay? We can simplify the numerator a little bit here, so we can make this a little bit cleaner, but that's it. That is the derivative. And remember, you're trying to find where that is 0. So I'm going to go ahead and set this to 0. You don't always set derivatives to 0, right? But we do a lot, because we're trying to find, again, where the rate of change, right, where the slope of the tangent line is 0. So we have to solve this equation. Ultimately, we have to solve this equation. That looks like a challenging equation to solve, but it's not as hard as it looks. All right, let's simplify the numerator here a little bit. So 2x times x minus 2, that's 2x squared minus 4x, and then minus x squared, right? Minus x squared times 1 over, don't worry about squaring out the x minus 2, just leave it in factored form. And let's keep this equal to 0 because we ultimately have to find the solutions to this equation, right? We have to find the x's that make this equal to 0. Well, this simplifies a little bit, right? 2x squared minus x squared is, that's just 1x squared, right? So you have x squared minus 4x over x minus 2 squared equal, and then all of that's equal 0. So you've got to solve this equation where you have this fraction equals 0. Okay, this is such an important fact to remember from algebra, but students tend to forget it a lot, okay? When you have a quotient that equals 0, so a fraction that equals 0, that can only happen when the top is 0, because the bottom cannot be 0, because you cannot divide by 0. So you can only have this fraction equaling 0 if the top is 0. So you can just sort of drop the denominator. Isn't that convenient? So we just have x squared minus 4x equal 0. That's the only way this fraction can come out to be 0. But now this is an easy equation to solve by factoring. Factor out x, and so you get x times x minus 4 equals 0. And that means x equals 0 or x minus 4 equal 0. And there are your two x values where you're going to have horizontal tangent lines. See, we already spotted those a moment ago, right? When we looked at the graph, we knew it was 0 and 4, but now there we found it with pencil and paper, with calculus, okay? So we don't have to rely on making a graph. All right, we can do this by hand. So we know we're going to have a horizontal tangent line where x equals 0 and another horizontal tangent line where x equals 4. Now they actually want the points, so they want coordinates. So when you're typing in the answer here in WebAssign, you would have to plug the 0 back into this function to get the y coordinate, right? That turns out to be 0. And you'd have to plug the 4 back into this function to get the y coordinate. Apparently that turns out to be 8, okay? That's what we saw on the graph, but you could do that arithmetic. So you get the point 0, 0, and 4, 8, all right? So that is a very common problem in calculus, all right? Where are tangent lines horizontal? Because that is the same as asking, where are there peak and valley points on the graph? And those are points that are often of interest to us for many reasons, okay? So we look for those points on the graph a lot. So this very process of setting the derivative to 0, we do that a lot in calculus. That's very common. All right, so are there questions about that one? Saad, was that one you asked? Was that one?
Yes, Professor, that was one of the questions that I had asked.
Yeah, so now you see how to do that one, right? You probably figured that one out by yourself, okay? But anyway, there's how you do that. Now, Saad, did you send me this one also? This one's harder.
Yes, this one also I did.
Yeah, okay, this one really is tricky. It's when you see it done, then it becomes easy, but it's just figuring out what they're asking is actually I think the hardest part of this problem. Okay, so it's really a good problem though, because it really sort of tests your knowledge of a couple of things. All right, so they want you to use graphs. That's kind of interesting to find. They want you to use the graphs of these two functions. Okay, let me say that again. They've got the graphs of these two functions, f and g, right? Okay, and so what they're going to do is form a new function by taking the product of f and g, but you don't know what the formula for f and g are, right? So you don't know what the formula for this function p is. All you know is that p is the product of f times g, okay? But you don't have the formulas for f and g, you just have their graphs. So you don't have the formula for p. And then they're going to do the same thing. They're going to take the quotient. So I guess p is for product here. And then they're going to also take the quotient of f and g to form a new function they're calling q, which I guess is for quotient. And but you don't have the formula for f and you don't have the formula for g. You just have their graphs, right? So you don't know what the formula for this function q is actually. But then they're going to ask you questions about the function P and the function Q that you really don't know much about, right? And first thing is they want you to find what is not P of 4. They're not asking for P of 4, but they're asking what is P prime of 4. That's the rate of change of this function P. Again, at x equal 4. There's x equal 4, so we can see x equal 4 on the graph. But how in the world do we find the rate of change of P at x equals 4? We don't even have a graph of the function P, and we don't even have a formula for the function P, okay? All we know is that P is the product of F and G, for which we have these graphs. All right, let me back up a little bit and let me ask you an easier problem before we attack the harder problem. Suppose they wanted to know not P prime of 4, but they just wanted to know P of 4. So what is the function P when you use x equals 4? What's the output when x equals 4? So not the rate of change. They're asking you the rate of change here, but we just want to know something easier. What is P of 4, not P prime of 4? Well, let me show you. That's kind of instructive because that's going to help you with figuring out what P prime of 4 is. Look, how is the function P created? It's F times G, right? So you know P of 4 is going to be F of 4 times G of 4. Whatever, however the function F works, however the function G works, P of 4 is going to be F of 4 times G of 4 because that's how the function P was created as the product of these two functions. But we know what F of 4 is. That we can figure out because we have the graph of F. All right, we don't have a formula for F, so we can't plug a 4 into a formula, but we can look at the graph. There's x equals 4, and if you go up to the function F, what does that look like? Is that 7 right there, I think? Yeah. When x equals 4, you get 7, halfway between 6 and 8. So F of 4 is 7. And what's G of 4? Well, here's the graph for G. There's 4. Go up, and it looks like that is what? 3? Yes. So it looks like G of 4 is 3, and you get 21. Oh, cool. See, that was really pretty easy. So P of 4 is 7 times 3, or 21, just looking at the graph for F and G. All right. But that's just P of 4. What in the world is the rate of change at 4? Okay, so what's P prime of 4? This is where now you have to remember the product rule, because remember, P is the product of F and G. And so that means that you can find the rate of change for P by using the product rule. Let's see, what would the product rule tell me here then is P prime of 4. Remember, how does the product rule work? You take the derivative of the first factor, right, times the second. So you would have, let's see here, F prime of 4 times G of 4. Okay, see how I did that? You take derivative of the first one and then keep the second one. So to find P prime of 4, that would be F prime of 4, derivative of the first one, times keep the second one. Plus, now remember you alternate, right? So you would do F of 4, keep the F, and then times G prime of 4. Now, some of this now I know because just a moment ago, we figured out what G of 4 was, right? G of 4, we said, oh, that's 3, cool. So I can start filling this in. So I have F prime of 4 times 3. All right, so that's better than nothing. And then I have F of 4, but remember, I figured out a moment ago that was by looking at the graphs, right? I figured out a moment ago that was 7. So for F of 4, I can fill in 7 times and then G prime of 4. Oh, so I kind of halfway filled in things here, but not quite completely, right? All right, so now this leaves me with one final thing I have to figure out. what is f prime of 4 and what is g prime of 4. I've got to figure that out before I can plug values in, right? And I can finish this arithmetic then, and then I can figure out what p prime of 4 is. All right, let's look back at the graphs now. So here's the graph of the function f, and there's the input 4, right? Now, what do you notice about the graph of the function f where x equal 4 is? What is that? What kind of curve is that? Right here where x equals 4, this piece right here. That's where x equals 4, right? X equals 4 is right there. So this piece of the graph of f, what kind of a curve is that? What would you call that?
Just
Looks
a
like a
straight
what?
line.
That's a straight, yeah, Lance, right? Okay, right. All right. Yeah, that's a straight line, Lance. All right. And straight lines are our favorite types of functions, right? Because they're just so easy to think about. And we know already what the rate of change of a straight line is. For a straight line, its rate of change, its derivative is the same as its what? Lance?
Slope.
Slope, yes, right, okay. So when they're asking for f prime of 4, that looks all very fancy, right? Okay, but it's not, because right here, f at x equals 4, right here, f is just a straight line. So you know that, oh, that derivative just has to be the slope of that straight line. So if I can compute the slope of that straight line, then I'm going to be able to fill that in. I think the slope, by the way, of that straight line, so you can calculate that, right? By using the slope formula, correct, and picking 2 points off of this piece of the line. But I think that turns out to be, looks to me like -1. Yeah, does that right look right to y'all there? Okay. I'm not actually doing any calculations. I'm just looking here at what's happening when x goes up by 1. It looks like y is going down by 1, right? You're stepping down by 1 each time. So that means the slope is -1. But you can also pick 2 points off of the line and use the, you can pick 2 points off of the line and use the slope formula, and you'll get -1. So f prime of 4 is just -1. And then for g prime of 4, well, let's look. Right here at x equals 4, what does the function g look like? It's this. And that's a straight line again, right? And that's not just any straight line. What kind of straight line is that? Right here where x equals 4, there's x equals 4. So what kind of straight line are we dealing with for g? Someone? Did someone say it? Someone chat it for me there. Yeah, what kind of straight line is this?
It's a zero slope.
Zero slope, right, Colin? That's a horizontal line, right? So that has zero slope. So for g prime of 4, you can just fill in 0. That's all you have to do. And so, oh, this turns out to be really easy. It's -3. So even though you don't know very little about the function p, you have no idea what its formula is. You have no idea what its graph looks like. Who knows what the graph looks like, right? Okay. But nevertheless, there is its rate of change at 4. It turns out to be got to be -3. Okay. So so even though we don't even have a graph of the function p, we know something about the function p at x equals 4. If you were to make a graph of p, that function would be decreasing. That curve would be going down because it has negative slope. Okay, so it would be going down here at x equals 4. All right. Now you can do part B the same way, but there you will have to use the quotient rule. All right, there you will use the quotient rule because the function q is the quotient of f and g. So you would use the quotient rule like we use the product rule here. Saad, was that one of your questions? Was that one
Yes,
of the
Professor.
questions? Does that make sense now?
Yes,
going on there?
definitely. It's clear now.
Yeah. Okay. So that one's a tricky one. That one is tricky because you have several things to think about there in that problem. Let's see. I think the next one is a little bit easier. They're asking us for. So I'm not going to do all the steps of this one. They're saying the velocity, not the position, but the velocity of an object is given by this formula. And then they're asking us, okay, so what's the velocity at when t equals 4? Well, that's easy. You just plug 4 into this formula, right? So you get 31 minus 4 squared, which would be 31 minus 16 or 15. So that's easy to fill in, okay? But the harder part is, what's the acceleration when t equal 4, okay? But remember, acceleration is the rate of change of the velocity. So acceleration is the derivative of the velocity. So keep that in mind. In physics, acceleration is derivative of velocity. Velocity is the derivative of the position function. But they didn't tell us the position function here. They just told us the velocity function. So to find a of 4, you just have to take the derivative of b. So that formula for that would be minus 2t, okay? Because the derivative of 31 is 0, and the derivative of minus t squared is minus 2t. So a of 4 would be minus 8, minus 2 times 4, okay? This third part is very confusing, so I'm not even going to try to go into that one. I don't like their explanation for this third part at all. So, all right, 2 other problems. Let's take the easier one first, and then we'll look at this is a famous curve called the Witch of Agnesi. And Maria Agnesi, I think it was Maria Agnesi, is a mathematician, a woman mathematician actually, from the Middle Ages, and she studied properties of curves like this one, and so it's named after her. It's not that Maria Agnesi was a witch. This curve is called the witch, right? And all right, but before we look at that one, let's look at the last one. This was really easy, but maybe it was confusing by the way it was asked. They want to find f triple prime of x. That is the third derivative. Okay. But they're not giving you the original function. They're giving you the second derivative. So that's actually convenient, because the third derivative is just the derivative of the second derivative. So to find f triple prime of x, the third derivative at x, you just take the derivative of f double prime. So this is just a differentiation problem. Let's rewrite this formula for the second derivative. Instead of 2 minus 7 over x, I'm going to write this as 2 minus 7 times x to the minus 1. I'm going to pull the x up to the numerator and write that with a negative exponent, because that makes it easier to find the, whoops, what did I do there? That makes it, yikes. I'm winking in and out here. That makes it easier to find the, make sure my power is plugged in, but it is. Okay, that makes it easier to find the derivative if I write this fraction with a negative exponent. So the derivative here would be the derivative of 2, which is 0. And then on this term, you just apply the power rule. So you bring the minus 1 down. So you have minus 1 times minus 7, and then x to the subtract 1 from the exponent. So you get x to the minus 2. And now, of course, minus 1 times minus 7 is positive 7. So you have 7x to the minus 2. And now you can bring the x to the minus 2 back to the denominator and write that with a positive exponent. So you end up with 7 over x squared. So 7 over x squared would be the answer here. All right, so now let's look at the Witch of Agnesi. So they're asking us for the equation of the tangent line at this given point, which I guess must be this point. 2, 1. Can we draw that tangent line? Am I going to be able to draw that very well? Oh, kind of. So there's my rough sketch of the tangent line there at the point 2, 1. Okay, but we don't have to make a rough sketch. We can actually find the equation for this tangent line, and then we could actually graph that equation, and we could come up with just a perfect graph of the tangent line here to 5 over x squared plus 1 right there at that point 2, 1, right? So to write down an equation for a line, right, you always need what? What basic information do you need to write down the equation for a line? So we've talked about this now many times. What pieces of information do you need to write down the equation for a line?
Slope and the points.
The
and maybe
slope
the
and a point, right? Okay. Just if you know the slope, Saad, you only need to know 1 point. Usually, to find the slope, you need 2 points, right? Anyway, but if for some reason you know the slope, then if for some other reason you know the slope, you don't even need 2 points. You just need the slope and 1 point. Okay. So we know a point, right? 2, 1 is our point that is on the tangent line, correct? And then the other thing we need is the slope or another point. But Saad, here we know the slope, or we're going to be able to find the slope because how do you find slopes of tangent lines?
If you get the derivative of 5 over x squared plus 1, that would be the slope of 2, 1.
That's right. Yeah, you find it from the derivative, correct? So derivatives, rates of change, slopes of tangent lines, all the same thing. So we have to find here f prime of x, right? And then we'll plug in 2 in for x into that formula, and then that will give us the slope, and then we'll be on our way, right? So here we just need to find the rate of change of this function, and there we can use the quotient rule, right? So I take what? The derivative of the top times the bottom, but the derivative of 5 is 0. So I get 0 times x squared plus 1, and then minus, and then keep the 5, right? And take the derivative of x squared plus 1. That's nice. That is 2x. And then keep that all over x squared plus 1 squared. I forgot all of the things that Maria Agnesi studied about this particular type of curve. She learned lots of things. This curve has lots of unusual properties that she studied, but Maria Agnesi predates calculus. So Maria Agnesi did not know anything about calculus when she was studying curves like this one. And so she learned all of the things that she did about these curves just through geometric intuition, not by using fancy tools like we're using, like calculus. All right, so let's see, what does the numerator turn out to be here? This is 0. And so you get what? Minus 10x over x squared plus 1 squared. And now you're going to plug 2 in for x, right? So you're going to calculate f prime of 2, plug that into this formula, and that looks like it's going to be minus 10 times 2 over, and then 2 squared plus 1 squared, so that is 5 squared. So we end up with minus 20 over 25, which reduces to minus 4/5. So the slope that for our tangent line is, there it is, minus 4/5. And now you can easily write down the equation for the line, right? It's going to be y equal to this slope minus 4/5 times x minus the x coordinate of a point. Well, here's our point. And then just add on the y coordinate of the point. So that's all very fast, right? There is the equation for this tangent line at this point. Okay, so there's the actual formula. So that's another type of problem that will show up there frequently. Frequently that will show up probably frequently in your homework, and then that will be on, certainly something like that will be on the test. So if you look at the sample test, I'm sure there's a problem that's stated similarly to this one. Maybe not exactly the same, but it's going to be essentially the same problem. Okay, all right. Do y'all have so there were some of the problems that people missed. Do y'all have any other questions that you want to ask here quickly before we go back and look at the notes and finish up the chain rule? All right, what time are we at here? Okay, so I think we've got enough time here to so don't let me just blow past you here. If you've got questions, just go ahead and express them. We just have two more examples here with the chain rule, and in these problems, remember, we were finding the second derivative of a function. Well, you know how to find second derivative of a function, right? So this really wasn't a question about second derivatives. It was really a question about using the chain rule. So let's look at, just as a little reminder of the chain rule here, let's look at B, and then I'll have y'all maybe attack part C, okay? When we take our break. So let's do this one quickly. We want to find, well, let's see how quickly we can do it. I'm not sure we can do it, but we'll try to do it. We want to find the second derivative of sine of x squared. Notice this is not the same as sine squared of x, right? So those two formulas are not the same thing, right? Remember, this means that you would take sine of x first and then square it. But this means you square x first and then you take the sine, okay? So the order of operations are different on the left here and on the right, okay? But we're not interested in this one. We want to find the derivative of sine of x squared. But when you say that, when you read that off of the page, by the way, it reads kind of the same way, right? All right, so to find the second derivative, we have to find the first derivative first, right? You have to go through the first derivative to get the second derivative. So let's see if we can find first derivative of sine of x squared in parentheses here, right? And so remember, this is an opportunity for the chain rule. This is one of our key places where the chain rule is going to come into play, because we have sine of an expression, right? Sine of an expression is more complicated than just x. Not much more complicated than x, but it's x squared, right? Okay, so a little bit worse than x. So so the chain rule says, remember, right, that you're going to just start off like you were computing the derivative of sine, which is cosine. So that's easy enough. So you get cosine of x squared, and then what's the little catch here? There's always a catch, right? What's the catch that you have? So what's the thing that you have to do to complete this derivative properly? So I've already written, I'm going to multiply something. What do I have to multiply in here to make sure I get this derivative correct?
The equation inside the parentheses?
Yeah, the derivative of the equation inside parentheses column, right? Yeah, so you have to take the derivative of this expression, all right? So what is the derivative of x squared?
2x.
Say that again.
2x.
2x, yeah. So we just have to finish this off by multiplying in a 2x. See, if your original function, if the original function were just plain old vanilla sine of x, right? Then of course, as we've said 100 times now, the derivative would just be cosine of x, right? But that's because you're taking sine of just the expression x, right? But if you have an expression that's more complicated than just x, then you have to multiply in, you take the cosine, but then you have to multiply in the derivative. That is the essence of the chain rule. Actually, in a way, you're also applying the chain rule here. It's just invisible to you. Think about what we did here. To find the derivative of sine of x, we took cosine of x, and then you can think of multiplying in the derivative of x, but what is the derivative of x?
1.
1. So in a way, we also use the chain rule here, okay, right? It's just that the what we multiplied in here was just 1, so we don't notice any effect. But here, we do notice an effect, right? Okay, we take cosine of x squared, because the derivative of sine is cosine, and then we have to multiply in the derivative of x squared. All right, so we end up there with 2x. I'm going to write the 2x in front. So 2x cosine of x squared. Now, that's the first derivative. However, in this problem, we were not asked for the first derivative. We were asked for the second derivative. So darn it, we have to do this again, okay? So we have a little bit more work to do, all right, before we're finished. All right, so we're going to now take the derivative here. Okay, but now what rules are we going to use to find the, so which of our differentiation rules are we going to use to find the derivative here? Notice, how is this formula formed? It's formed as begins with a P. So
Polynomial?
it's not a polynomial. Good guess, though. Okay, polynomials don't have trig in them. All right, so polynomials are kind of the opposite of trig. Polynomials just have arithmetic in the formula, no trig. So not a polynomial, but what else begins with a P there? Yeah, what operation are we performing to form this formula? There's actually several operations, but one of them is really kind of right in the middle here of forming this formula.
Product rule?
Product rule, that's right, it's the product rule. Because see, to form that formula, right, you are multiplying things together, correct? What I'm going to think of as multiplying together is 2x times cosine of x squared. See, you're forming, you're creating that formula through a product. You're also doing other things in the formula, right? But sort of right there, key is this product. There's your first factor, and here is your second factor. So those are the sorts of things you have to kind of recognize when you're trying to differentiate an expression, a formula. You have to sort of look at it and think about what's the structure of that formula, okay? And what a rule will help me with differentiating that formula. Here we can see this formula is a product of two things, and so there I can use the product rule. Now, it won't be just the product rule, but that's where we'll start. Okay, so I'm going to use the product rule. So what does the product rule say? Let's see. I have to take the derivative of 2x and then multiply it by, keep the cosine of x squared. What is the derivative of 2x?
Is that 2?
2, yes. Great. And then just keep the cosine x squared, right? And then plus, keep the 2x, right? And now, whoops, here's where things get a little bit tougher. Now you have to multiply in the derivative of the second part, which is cosine x squared. All right, so I've got to multiply in here. I can get my pen to write. I've got to multiply in here, right pen. I've got to multiply in here now the derivative of cosine of x squared. See, that was kind of like the derivative of sine of x squared, right? So we're going to kind of repeat what we did up here originally, but not quite the same because this is cosine instead of sine. Well, so how do I find the derivative of cosine of x squared? Oh, I think I know how to do that. What's the derivative of cosine? That you just have to have memorized. So what's the derivative of cosine?
Negative sign?
Negative sine. So you write in here minus sine, keep the x squared, but then Colin, this is where we always have to slow ourselves down and not get carried away too fast. I have to multiply in then the derivative of what? What's inside the parentheses here, right? Because that is not just x. it's x squared. So I have to multiply the derivative of x squared, which is what we said above
2x.
was 2x. There you go. So you get an additional factor of 2x. So you have 2 cosine x squared. Let's see, 2x times this minus sign. I guess that's minus 4x squared. And then sine x squared. This one I can simplify. Well, no, I can't. Okay, so let's just leave it like this. So there's our second derivative. All right. Okay. So wow, that was in finding that second derivative. After we found the first derivative, in finding the second derivative, we had to use the product rule, but we also had to use the chain rule again when we found the derivative of cosine of x squared. All right, so let's try this one. Again, we have to find second derivative. So that means we have to find the first derivative first. That may be already hard enough, right? Okay, so got to find the first derivative first. And the first thing I'm going to do here is rewrite this with fractional exponents. So this is just a standard practice when you're finding derivatives. You want to get rid of square roots, okay? So how do we get rid of the square root? What do we convert that to?
Fraction.
Exactly. So this is 1 over 2x plus 1 to the 1/2 power. And now I want to get the, I can get rid of this fraction. So let's bring the 1/2 power up. And I can do that by making that a negative exponent. So 1 over 2x plus 1 to the 1/2 power is the same as 2x plus 1 to the minus 1/2 power. So I haven't even found the derivative yet. Haven't even started with finding the derivative yet. But I was just rewriting the original formula just to make it easier for me to find the derivative. Okay. All right, so working from here, let's find the first derivative. Okay, where do we start? What rule are we going to use there? It's not the product rule, but it sounds like the product rule. What rule will we use here to find the derivative? When I say it sounds like the product rule, that's because it begins with P. So what's the other derivative rule we know that begins with P?
Power rule?
Power rule, exactly. We're going to use the power rule here. So you just have this expression, 2x plus 1 raised to a power. So we can use the power rule just right straight away. We have minus 1/2 2x plus 1 to the minus 1/2 minus 1. Let me write that down so we can make sure we do that arithmetic right. But now look, that's not the answer because I have to now multiply something else in here. What can I not forget to multiply in? See, when we use the power rule, this is not just x raised to a power. It's this expression, 2x plus 1 raised to a power. So that's more complicated than just x raised to a power. So you can use the power rule just like you normally would, but because you have 2x plus 1, not just x raised to the power, you have to multiply in at the end here, what, to make this correct? So Damien or Daniel, either of the two Daniels, what do I multiply in at the end?
Was 2x?
Not 2x, almost, Daniel, but you're on the right track. Where'd you get the 2x from?
The derivative inside the parentheses?
Yeah, the derivative inside parentheses, but what's the derivative of 2x plus 1? you went a little bit overboard with 2x. What's the derivative of 2x plus 1?
It's still 2x. I don't know.
No, it's just 2. Yeah, it's just 2. Okay. Yeah, the derivative of 2x is just 2. The derivative of x squared is 2x, but the derivative of 2x is just 2. Of course, the derivative of 1 is 0. So you had the right idea. You have to multiply in the derivative of 2x plus 1. But the derivative of 2x plus 1 is just 2. Okay. So there is the correct first derivative. Let's see. I'm going to take the 2 and multiply it by the minus 1/2 because that just gives me minus 1. So I have minus 1 times 2x plus 1 to the now minus 1/2 minus 1 is minus 3/2. Now I'm not going to worry yet how to convert the minus 3/2 back to a radical. Not going to worry about that yet because we're not even done with the problem. Remember, what we want to find here is not the first derivative. We want to find the second derivative, right? So now we have to take the derivative of all of this. So I've got to kind of repeat this process now, right? Okay. Now I want to find the derivative of the minus. Don't forget the minus is in front here. 2x plus 1 to the minus 3/2 power. Okay. All right. So I'm going to let y'all try that one. Find the derivative of, so we can finish this off with the second derivative, right? Find the derivative of this quantity, the first derivative, right? That will be the second derivative. So you can follow kind of these same steps. It's going to look, it's not going to be the same, of course, but it's going to look very similar, finding the second derivative to what we did to find the first derivative. Okay. All right. So I'm going to give you all 5 or 6 minutes. We'll take a break here at the same time. See if y'all can write down that second derivative. Let me pause the tape here for a moment, and then we'll come back. Okay, so I resumed the recording there. So let's see if we can finish off this this last example of the chain rule, right? So we wanted to find the second derivative, and that means we have to find the derivative of the first derivative. So there's the first derivative, minus 2x plus 1 to the minus 3/2 power. So let's see if we can repeat that process that we used for the first derivative to find the second derivative. Someone want to help me here, volunteer to tell me what to do here to find the derivative of minus and then the 2x plus 1 to the minus 3/2 power? Where would what do I start there? How do I start that process? I want to make sure I'm checking off everyone today who's been helping me. I remember everybody. Okay, so how do we just find this? How do we find this second derivative? What's the first step there in finding the second derivative, in finding the derivative of this formula? Exactly, Zachary, that's right. So we're going to use that's the power rule, Zachary. So we'll take the minus 3/2 and we're going to bring that down in front, right? So I have this, the minus that's already there, and then I'll have also the minus 3/2 brought down, right? And then times 2x plus 1 to the, and now, Zachary, what do we do with that exponent? This minus 3/2 here? Yeah, subtract 1, right? So we end up with minus 3/2 minus 1. But now, Zachary, here's the key thing, though, okay? That's just the power rule. But unfortunately, the power rule here is a little bit extra complicated because, again, just like when we were finding the first derivative, right? This is not just x to this power. It's 2x plus 1 raised to the power. So what do I have to multiply in here extra? Right at the end. Multiply by 2, right? Which is the derivative of 2x plus 1. So you have to multiply in here the derivative of 2x plus 1, which is 2. And that's it. So really, there is the formula. That is the formula for the second derivative. Now, we can clean that up a little bit. Let's see. We have a minus and a minus, right? So those are going to cancel. The 2 and this 2 will divide out. So it looks like we end up here with a coefficient of just 3. That's nice. So we get 3 times 2x plus 1. And then we have the minus to the minus 5/2. So there's a little bit better version of the second derivative. Of course, you can write this as 3 over 2x plus 1 to the positive 5/2 by making that negative exponent positive, right? And moving this to the denominator. Don't move the 3, but just the 2x plus 1, right? Move that down to the denominator and you get a positive 5/2 as the exponent. And now you can convert that back to a radical. So this is 3 over, when you have an exponent of 5/2, remember the 2 is going to tell you the type of root. So you would have square root of, the 2 in the denominator tells you this is square root. So you have square root of 2x plus 1. And now the 5 will stay as an exponent. So you have square root of 2x plus 1 to the 5th power. Keep the 5 as exponent. We could simplify this a little bit further, actually, because you are able to extract a square root of a 5th power, but I'm not going to go through those steps. So let's just leave it like this. This is clean enough, I think, for us to use. So we have 3 over square root of 2x plus 1 to the 5th power. There it is. That's the second derivative, right? Okay. So see, it's just a combination of rules, right? The power rule, the product rule, and then this part with here, which that's the chain rule. That's what's known as the chain rule. But the individually, the power rule, the product rule, the chain rule, they're not that bad. Okay. It's just that you have to remember to combine them sometimes, right, in the same problem. Okay, all right. So, well, we just have to rely on your homework now. Your chain rule homework that's due next Tuesday to give you a little bit better practice, right, in using the chain rules. So, but remember, in the process of using the chain rule, you might have to use the product rule or the power rule, or maybe even the quotient rule as well. Okay, so you may have problems that combine several of the rules at one time. All right. Okay, so let's look at the second thing that we wanted to talk about today. So I'm switching notes here. We want to talk about what's called implicit differentiation, and I'm going to explain. So implicit differentiation is just another form of differentiation. We're not going to be learning any new differentiation rules here. Actually, we're finished for the course in learning new differentiation rules. So you really are very skilled now at doing differentiation. There's only a few types of functions right now that you cannot differentiate. Okay, so you're almost a master at differentiation now. So this is not a matter of learning any new differentiation rules, implicit differentiation, but let me show you how it's useful. So up until most of the time in this course, when we have had a formula for a function written down, that's been of course, that's an equation, right? Okay. And usually the equation is solved for y, right? The output variable y. And like, for instance, here's an example of a very simple function formula, right? Where you just have y equals and then some expression involving x. Here it's a very simple expression, just 1 over x. So when you have a function, a formula, and it is solved for y, that's called explicit form. But it turns out that in many instances, it's you can write down a function formula, that is the equation for a function, but sometimes it's more convenient for the to not have the equation solved for the variable y. Okay, so in many cases we do have the equation solved for y, but in some cases it's easier to write the equation down and not have it solved for y. Now, this is not an example of such a situation. Okay, I'll show you an example in a moment of such a situation, but let me show you. This equation does not have to be solved for y. Okay, so there are lots of different ways you can rewrite this same equation. One easy way is to just multiply both sides of this equation by x, right? And if you multiply both sides of the equation by x, you get this equation: x times y equals 1. That's the same formula, okay? Right? That's the same equation. It's just written differently. So when you graph this equation, you're going to get the same picture as when you graph this equation, okay? So both of these equations represent exactly the same function. But notice this one is not solved for the variable y. So when you have an equation not solved for the variable y, that's called implicit form. Implicit form. So this is, did I write this down here? This is explicit form, solved for y. And this equation, which is the same equation, would be called implicit. And again, in some instances, not this one, but in some instances, it's easier to write down the formula for a function in implicit form, okay? And now, if we have a function formula written in implicit form, it's still a function, so it still has a derivative, okay? You know, it still has a rate of change. And so, so the object of this lesson is to learn how to find derivatives for functions when they're not written in explicit form, when they're written in a form like this. Again, that's called implicit form. Now, in the notes, well, so what I just said is all just written out in words here in the notes, okay? So if you read the notes, this just is going to repeat what I just said. In the notes, there's a step-by-step process for finding derivatives for functions written in implicit form, okay? This process is called, not surprisingly, implicit differentiation, all right? I'm not going to read these steps off to you one by one, but we're going to learn them by practicing them, okay? So what I'm getting ready to practice is just these steps, but if you want to, the steps are written out in the notes, okay? All right, so let's use that example that I just showed you of implicit versus explicit form, and let's find the derivative function both ways, okay? So remember, I had this function y equals 1 over x. Here's one way of writing the equation. So that's the explicit way of writing the equation for the function. That means we're solved for the variable y, right? Here's the implicit way of writing the same equation, not solved for the variable y, okay? And now let's find the derivative both ways, okay? With the equation originally written like this and with the equation written like this, okay? Well, let's start with what we already know. We know how to find the derivative when the function is written in what's called explicit form, right? Solved for y. So very easy to find the derivative here. So you can write that down as dy over dx. That means the derivative, or you can also write that down as y prime. That's another way of writing the derivative. So let's see, what would be the derivative here? Well, 1 over x means x to the minus 1, correct? X to the minus 1 is the same as 1 over x, right? And if you write 1 over x is x to the minus 1, then you can use the power rule, right? So you would bring the minus 1 down and then subtract 1. So you would get minus x to the minus 2. And of course, that's minus 1 over x squared. So really fast, right? Okay. So very easy. All right, but let's try finding the derivative.
Audio.
Professor, can you hear me? Okay, we can't hear you. Oh no, okay. Okay. Go ahead and
I
talk,
think we can hear you now.
Professor.
What?
Oh, we can hear
We
you
can
now.
hear you now.
You're good.
Oh, I'm back.
Mhm.
Okay. All right. So,
Good.
okay. All right, let me get rid of this. Okay, so well, y'all saw me take the, I don't know how much you heard, but you saw me take the first derivative here written in when it was written in explicit form. If I start, am I still on? Can you still hear me?
Yes, we can still hear you.
As soon as if I blink out again, please message me, all right, and tell me that
We'll do.
that you can't hear me again. All right. Okay. So now I want to show you writing down the derivative when the formula is written in implicit form. Okay. So let me show you the steps that we're going to have to go through here. Okay. So what we're going to do is write down the equation, and we're going to take the derivative of both sides of the equation. So we're going to take the derivative of the left and the right. We're going to take the derivative with respect to x. Okay, that's really important. You're thinking of x as the independent or the input variable here. Remember, y is the output variable. Y is a function of x. That's how we're thinking of this equation, of this situation. So now, when you take the derivative of both sides of the equation, the right-hand side is really easy to differentiate, because what's the derivative of 1? That is a constant. So what's the derivative of 1?
0.
What's the derivative of a constant always? What?
0.
0, right. So so this is the easy part. The derivative of the right-hand side there is 1, right? So you're going to differentiate both sides of the equation. So this side trivial, it's 0. This side now is trickier, okay? first thing I want you to notice is, ooh, we have a product here, all right? On the left-hand side, we have x times y. That is a product, and that means we're gonna have to use what? What rule? When you have
Product.
products, what?
Product rule?
The product rule, right? Okay, yeah. I was trying to make that very obvious. All right, so it's the product rule we're gonna have to use, okay? All right, so let's think now about using the product rule. Well, so we practice that now a lot. So let's see, first we take the derivative of x times y. Remember, you're taking the derivative with respect to x. X is the variable here. So what is the derivative of x though? What's the derivative of just plain x? See, these are the two things that are multiplied together. X and y.
1.
What now? Y'all said it. What? Son?
Is it 1?
1. Yeah, right. Okay. So you have the derivative of x, which is 1, and then you keep the y, right? Okay. Just keep the y because that's the second thing that you're multiplying. Plus, now you switch that, right? So you keep the x, and now you want to find the derivative of y. All right. But look, all right, this is where things get really clever or also confusing. We want to find the derivative of y. But look, that's what the problem is all about, finding the derivative of y, correct? So, you know, it seems like I'm in a circle here. I need the derivative of y in order to find the derivative of y, right? Okay. So it looks like you have, it looks like you've reached a dead end. Now, you haven't reached a dead end. Just pretend for a moment here that you know the derivative of y. So let's just write that down, okay? How do we denote the derivative of y? We denote it by y prime. You see the game that we played there, okay? I have derivative of x times
Sorry, that's crazy.
yeah, that's crazy, but
I'm having a hard time with it.
All right, so lots of things at math are crazy, but you're gonna see that it's gonna have a happy ending here, right? Okay. Look, now you keep the x and multiply by the derivative of y, which you don't know, unfortunately, at this point, because that's the whole point of the problem. So we'll just write down derivative of y. Okay, so there's my notation, Colin, for derivative of y, correct? Or you could write dy over dx if you want to right here. Okay. But look, Colin, here's what I'm going to do now. I have an equation here, okay? Because I have all of this is equal to 0. So I can solve this equation for y prime, okay? So that's what I want to do. So let's see if we can do that. How do I solve this equation for y prime?
You can bring the 1y over.
So I get x times y prime equals, what is that, minus y? 1 times y is just y. Bring that over, that becomes minus y, correct?
Right.
Now divide by what?
X.
X. So I have y prime is equal to minus y over x. But remember, what was y originally? 1 over x, correct? So you have here minus 1 over x times x. I'm being divided by x, and that's minus 1 over x squared. So you end up there with same thing. Okay. Now,
Nope.
normally this step, we would leave off. Okay. So there we would use this expression. We would use this equation as our derivative. Let's try it again. Okay. that looks like that's kind of unbelievable. So let's try another example. Now, this example is much better because here's an example of a function that's very hard to write in explicit, explicit form. Okay, so here's my equation. Here's my equation: x squared minus 2y cubed minus 4y equals 3. So I claim when you graph that equation, here's the picture that you get. Okay, so there it is. So is that does that curve happen to be a function?
Yes.
Yes, that is a function, right? Because what, each x is going to match just one y, correct? So indeed, this this curve is a function. So when you graph this equation, that's the curve that you get, and that curve is a function. So so this equation really does represent a that equation really does represent a function. But that equation is very hard to solve for y. It's very hard to put that equation in explicit form. Just very difficult to do that because of the nature of the equation. Okay, so if you want to find rates of change for this curve, if you want to find derivatives for this curve, you're really stuck with using again this implicit differentiation process. You have to leave the equation in implicit form because it's very difficult to solve the equation for y. Okay. Well, let's see if we can try this then. So let's see what we're asked for here. It says find the derivative. So find dy dx, and then let's evaluate that derivative when x equals -3. So apparently when, let's look at the curve here. When x equals, there's -3 on the curve. So apparently when x equals -3, y is equal to 1. Okay, so the point -3 and 1 is on the curve. So let's see if we can find the rate of change or the derivative at this point. Or that would be the same as, let's see if we can find the slope of the tangent line at this point. By the way, is that going to be negative or is that going to be positive? So is the derivative here at -3, 1? Is that going to be negative or is that going to be positive?
Negative.
Negative. Colin, why do you know it's negative?
Well, because it's headed downward, left to right.
That's right. The curve is decreasing, right? So, you know, where curves are decreasing, they have negative rates of change. They have negative derivatives, right? So if you kind of imagine what the tangent line looks here, ooh, I really drew it awful. If you kind of imagine what the tangent line looks like right here, it's going to have negative slope, right? Okay. Maybe that's a little bit better. Yeah, so the tangent line looks something like this. It's going to have negative slope for sure, right? So the derivative is definitely going to be negative, but let's see if we can figure out exactly what it is. All right. So we're going to go through that. This is just the second time. So so watch me carefully. We're going to go through this implicit differentiation process. Okay. All right. So here's what you do. All right. So start with the equation. Just start with the equation that you're given. All right. And you're going to differentiate both sides of the equation. Remember, you're thinking of x as being the input variable, y is the output variable. So you're differentiating with respect to x. Okay. Well, x is the key variable here. So I'll do the I'll do the right hand side. I'm going to differentiate 3. Okay. So that's 0. All right. So I did half of it. All right. So y'all do the other half. All right. Well, that's much harder, right? Okay. So let's see if we can differentiate now the left hand side. Okay. All right. So wow. what about this first term, x squared? So what is the derivative of x squared? So we've done that now 50 times,
2x.
right? So what?
2x?
2x, right? So that's easy to start. You just get here 2x to start with, right? Now here's the tricky part. What is the derivative of minus 2y cubed? Okay, all right. So you're going to start this just exactly like you would expect, all right, using the power rule. So bring the 3 down, so you have minus 3 times the 2, right? You got this minus sign, you bring the 3 down. So you have minus 3 times the 2 times y to what power there?
2.
2, yeah. But now here's the part that is a little bit mind-blowing. Remember, y is a function of x. So you have to think of y as being a formula that involves x. Y is not x, okay? Y is some formula that involves x. And so guess what? We have to use the chain rule here. So I have to multiply in here the derivative of the y. What is the derivative of the y? I don't know. So I'm just going to write down, I'm going to pretend that I know, and I'm going to write down y prime. So when you differentiate 2y cubed, you get minus 3 times 2 times y squared times y prime. Does that make sense to anyone? No? Yes? Maybe?
That's weird.
It's weird. That's right. It is weird. Yeah. Okay. Actually, I remember when I was, so this has been a long time ago. So I remember learning implicit differentiation, and I remember thinking exactly the same thing. That is weird. Okay. But let's see if we can, let me see if I can clarify it a little bit, right? Why the chain rule comes in here. See, if you were differentiating x cubed, not y cubed, but x cubed, right? That would be so easy, right? When you differentiate that, you would just get 3 times x squared, right? Okay. But remember, if you have some formula, I don't know what that formula looks like, right? Okay. But if you have some formula involving x, let me write that down a little bit more clear. If you have some formula involving x, I don't know what that formula is. Let's call it f of x. And that formula is cubed. Then when you find the derivative, remember, well, you bring the 3 down and you keep the formula squared, right? Okay, running out of room here. You keep the formula squared. But then you have to remember, oh, this formula is more complicated than just x, so I have to multiply in the derivative of that formula. That's the chain rule. Exactly the same thing is happening here.
But can I ask a question?
Yes.
Okay, so if we just look at 2y cubed,
Mm-hmm.
right? Then we differentiate it, it would be 6y squared, right?
Right.
Now that would be the differ with respect to y, right?
Yes. Right.
Not x.
Not x. That's right.
Okay.
Colin, the thing you have to sort of, the thing that's implicit here, that's why they use the term implicit differentiation, is you have to remember y is not just itself. Y is some formula of x, right? I don't know what that formula is because I can't solve this equation for y. It's too hard. But it's some complicated formula involving x. You know, it could be x cubed minus 7 over 3x squared, or who knows what it is, right? Okay. So you really have, when you have 2y cubed, you really have some formula with x cubed, just like we had here, right? Which requires us to, at the end, multiply in the derivative of that formula. All right, so Colin, what's
Oh,
the
I was gonna
what's the
gonna-
derivative of minus 4y then?
minus 4y. Well, in this, what I was thinking is that we're differentiating with regard to x, right?
Yeah.
So if we just did minus 4, that would be the differentiation with regard to y, not with regard
Yes,
to x. So we'd
exactly.
have to put in the other thing. So it'd be like
Yes.
minus 4 times y prime.
Perfect. That's what it is. Okay. You're thinking of it exactly correctly. All right. So you guys
Okay.
listen to Colin because the way he's explaining it is really correct, or the way he's thinking about it is the correct way to think about it. Okay. If this were minus 4x, its derivative would be minus 4. All right. Okay. We've done that a million times, right? Okay. But it's minus 4y. All right. And so we have to write here minus 4y prime as the derivative. This is only half the problem though, okay? Because now I have to solve this blasted equation for y prime, okay? Because I want y prime equals something. I want the derivative equals something. So I have to now do, but the rest of this is algebra. The calculus has ended, and now I have to remember my algebra skills to solve this for y prime, okay? All right, well, let's see. How do I solve this for y prime? So look, these two terms have y prime in them, right? This one does not. So move the 2x to the other side. You can move it to the right-hand side. So you have minus 6, minus 3 times 2 is minus 6. Minus 6 y squared times y prime minus 4 times y prime equals to minus 2x. All right, so take the 2x because it doesn't have y prime in it. Take that term, move it to the right-hand side. Now, these terms that are left on the left, they both have y prime in them, correct? Because that's why we left them on the left-hand side. Factor out the y prime. So you get from both of these terms. So factor y prime out here, factor y prime out here. You get minus 6y squared left, and then minus 4 equals minus 2x. Now to finish solving for y prime, that's easy. Divide both sides now by what's in the parentheses. So you end up with y prime equal minus 2x over minus 6y squared minus 4. There's your answer. That's the answer that we're going to go with, okay? So there's a formula for the derivative. Minus 2x over minus 6y squared minus 4. That's now the formula that we'll use to calculate rates of change. So let's see, what rate of change did we want to find? We wanted to find what? The rate of change at what? Minus 3, right? We wanted to find the slope of this tangent line. So what you can do is, how you can use that formula is plug minus 3 in for x, because that's the x coordinate at this point, and plug 1 in for y, because that's the y coordinate at this point. So you have minus 2 times minus 3, and then minus 6 times 1 squared minus 4. Let's see, what does this turn out to be then? In the top, you get 6, and it looks like in the bottom, you get minus 10. So it looks like minus 3/5. There it is. There is the slope of this tangent line is minus 3/5. So you notice, by the way, in this rate of change formula, it has both x and y. So both of those variables. So if you want to evaluate this formula, you have to have a value for x and a value for y. Fortunately, that's what we had in this in this problem, because we knew what the coordinates of this point were. We had both a coordinate for x and a coordinate for y. Ooh, all right. So let's try that one more time really quickly. Let's try another example. Oh boy. All right. So I think we have just time to start this. Okay. So we want to find a formula for a derivative dy dx for this curve. Let me show you what that curve looks like. Okay. Let me see if I can find it. I drew a graph of it. There it is. Ooh, nice curve. Okay. So we're going to find a formula for the derivative of this curve. By the way, what do you notice about that curve? That curve is not a what?
Function?
Not a function. Yeah. Okay. But we'll still be able to find, even though that's not a function, there it is, we're still going to be able to find rates of change. Okay. So we're still going to be able to find slopes of tangent lines. This curve still has tangent lines, even though it's not a function. This curve still has tangent lines at points. So we can use this implicit differentiation process to find tangent lines, slopes of tangent lines at points on curves, even when they're not functions. So that's one of the nice things about implicit differentiation, is it kind of expands our ability to do calculus now to curves that are not actually functions, like this one. All right, let's see if we can very quickly here start this. We just have 4 minutes. So let's see if we can go through the steps of finding, again, this some formula, some expression for the derivative for this curve, okay, this really complicated curve. When I'm going through this process, I'd like to use y prime instead of dy dx, okay, because this is kind of clumsy to write down. So I prefer to use y prime instead, but the book uses dy dx a lot. All right, so let's start this, okay? Remember, you're going to differentiate both sides of the equation, and this side is really easy because it's a constant. So what's the derivative of -4? It's a constant, 0. Exactly. Now let's try differentiating the left-hand side. So here we're differentiating the y cubed. So we'll use the power rule. So we'll have 3 times y squared. But since this is y, not x, what do I have to multiply in here?
Y prime.
Y prime. That is the chain rule. That's the chain rule. So what about for the second term? It's going to be 2y, bring the 2 down, times the y, and then times y prime, because this is y and not x. What about -5y? That is going to be -5y prime, okay? But this is easy because that is just x. So what's the derivative of minus x squared?
-2.
Minus 2x, right? Use the power rule. Bring the 2 down so you get -2x. And you don't have to multiply in x prime. X prime, by the way, is 1. So no sense in multiplying in a 1 there, right? So there is first step. We differentiated both sides of the equation. Now we have to solve the equation for y prime. Solve the equation for y prime. That this term doesn't have a y prime in it, so I'm going to get rid of it. I'm going to move it to the right-hand side. So I have 3y squared times y prime plus 2y times y prime minus 5y prime equals positive 2x. All of these terms left on the left-hand side have y prime in them, so you can factor that out. So you have y prime times 3y squared plus 2y minus 5 equals minus 2x. And now divide by this in the parentheses, both sides. So you get y prime equals minus 2x over 3y squared plus 2y minus 5. There you have it. So that is the formula we use for the derivative. Again, that's a little bit different from derivative formulas that we used before because this formula has both x and y in it. Okay.
Is that 2x supposed to be negative? I've got mine not.
Oh, no, it's not. I don't know why I got carried away there and made it negative all of a sudden. So it's positive. All right. We probably would have noticed that pretty quickly because we would have gotten, if we were looking at the curve and looking at values that we got from this derivative, the signs would be off, right? Okay, so we probably noticed that, this thing is increasing when it's supposed to be decreasing, or decreasing when it's supposed to be increasing, something like that, right? Okay, well, so there, we don't have time to, we're going to go further in this problem, but there at least is the expression for the derivative for that function. Now we can answer interesting questions like, where is the tangent line flat? So right there, right? Where is the tangent line flat? Where is the tangent line vertical? It's right vertical here and here, but where could we, how could we find that from the formula? Okay.
Wouldn't it also be vertical like on the edges of the downward part?
Oh yeah, here as well, right? Yeah, I overlooked that. So also vertical here, right? Okay. Cool. All right. Okay, so so we'll save that for next time, right? Okay. So I'll see y'all. So we're out of time now. I'll see y'all on Tuesday. Okay. And don't forget your chain rule homework is due on Tuesday. Thanks for helping me, Colin. You got a really good.
I got some help from Zachary, so that's good. I got some help from Zachary.
Oh, Zachary was helping you too? Okay, well, that's
Yeah.
great. All right. So I marked Zachary as well. So okay. All right. All right. So thanks, guys. I'll see y'all on Tuesday, right?
Thanks, Professor.
Bye.
Thank you. You have a good weekend.
Thank you, everyone. Have a nice weekend.
Thank you. Bye bye.
Bye.